طيب السلام عليكم يا شباب. Let's continue what we have talked last time about the ideal gas equation of a state and its modification. BV is equal to ZRT. We have talked last time that we have an ideal gas equation of a state. This equation actually can be applied at very low density of the gas without any error in calculating the specific volume of the gas. But actually, when the case is converted to the real gas situation under higher pressure, in this case, we cannot apply the ideal gas equation of a state. In this case, we have to use the modified equation BV is equal to ZRT. And Z is a compressibility factor which account actually for the real volume of the gas. This parameter Z is function of what we call the reduced pressure, which is the pressure divided by the critical pressure. Function of reduced temperature, which is temperature divided by critical temperature, and the function of the specific volume V reduced, which is the ratio between the specific volume divided by the critical specific volume. So when we have any of those three parameters, any two of them, like pressure, reduced pressure and reduced temperature, then we can use actually chart A15 to calculate the compressibility factor Z. And then we can apply the modified equation of state BV is equal to ZRT in order to calculate the actual volume of the gas in case actually if pressure and temperature are given in this situation. And we agreed last time regarding your exam, because usually you seek about information about this situation. So in your exam, actually, you will assume any condition as an ideal gas, and you will apply actually BV is equal to RT directly. Unless actually he asked you in this problem to calculate the properties using the modified equation of state BV is equal to ZRT. Or if he asked you actually, does this gas is a real gas or ideal gas? So that means actually we have to calculate the value of Z in this case, and we have to use the modified equation BV is equal to ZRT in this problem. Otherwise, we have to apply actually the ideal gas equation of state. طيب, this is the modification in case when we have to move actually from ideal gas to the situation for the real gas under high pressure or high density using the compressibility factor Z. There were actually other modification for the ideal gas equation of a state. Those modifications actually are based on actually the empirical calculation, or we call them actually as empirical equation. Empirical means that this equation has been generated actually based on experiments. So we have some gases, test different gases under different pressure, different temperature at a given temperature, and then we can get a curve, repeat the process actually at another given temperature, and so on for different gases. Then we can come up actually make a kind of curve fit. Then we can actually get a modified equation based on those experimental data. This modified equation should give actually more accurate value at higher pressure when we have a gas at higher pressure compared to the case of ideal gas equation of a state. Those empirical equations, the first equation, we call it actually the equation by van der Waal. This is called actually van der Waal equation. Which is actually a kind of modification of the ideal gas equation of a state. Actually, all the modification of the ideal gas equation of a state, considering van der Waal equation, we'll have also here other equation, Betti-Bregman equation, Benteke-Webruben equation, and also Virial equation. All of these equations just for your knowledge. Just to know actually that we have some modification for the ideal gas equation of a state that can be applied actually more accurate as compared to actually to the normal ideal gas equation of a state. But those equations are just for your knowledge. They will not be coming in your exam. And if it came to your exam, just I will give you this equation or this equation. We'll talk about them right now with the constant. And then actually we'll just substitute. So if temperature and the specific volume are given, just I will be substituting in the equation to calculate the pressure. And the equation itself with its constant will be given for you. But in your exam, we don't like to test you how to calculate or how to use the calculator. It's okay. So just what we want from you actually to know that there are actually some modification to the ideal equation of a state based on the experimental data. Those equation actually, the first equation, we call it actually the van der Waal equation. So let's look at this equation and see actually their accuracy compared to the ideal gas equation of a state. As I told you, just the empirical equation just based on شباب we have يعني to test different gases at a given pressure, let's say at a given temperature, then we change the pressure, and actually each time we calculate the value of the specific volume. So let's say at a given temperature we can give actually this curve. As we increase the pressure, we can measure the value of the specific volume of the gas while fixing actually the temperature at T1, let's say. Repeat this experiment again, change the pressure, and each time at fixed temperature, and each time we'll actually be recording the value of temperature specific volume V. And repeat this process, and then actually by the end we can make actually curve fitting like using Excel. This actually property is existing in Excel. Then we can get actually a generalized relation between pressure, specific volume, and temperature. This equation actually is a fit for the equation BV is equal to RT. Then actually some other constant will appear in this equation based on the curve fitting. So it's a simple curve fitting process. So those constant that you see here in this equation, the constant A and also the constant B, which are function of the critical pressure and the critical temperature, those are just actually based on the curve fitting. It does not have actually any kind of physical meaning, just based on the curve fit. But يعني this equation يا شباب here, which is the modification of the ideal gas equation of state, instead of P, it will be B plus parameter or another term which is called actually equal to A plus V square. This is based on the curve fit. This parameter A divided by V square account for the intermolecular force between the molecules at high pressure, which should be high in this case. We said BV equal to RT can be applied at lower values of pressure because the intermolecular force is very low in this case. But at higher pressure, the intermolecular force will be increased with this term. So this term is a kind of modification. So it will equal to A divided by specific volume V squared. And also the volume, the actual volume of the gas, in this case, we have another term which is the modification minus P. This term actually we account actually for the volume, actual volume of the molecules themselves. We said actually the ideal gas equation of a state has a problem in actually predicting the actual volume of the gas. So in this case, to account for the actual volume of the gas, we have to subtract the actual volume of the molecules themselves. Okay. In case of gas, actually we don't have intermolecular force. So in this case, the molecules are a little away from each other. So when we calculate the actual volume of the gas, we calculate the volume occupied by the gas, not the volume occupied by the molecules themselves. So in this case, we can just subtract this term. But what about the constant A and constant B? Those are actually function of the gas constant R. I is equal to 27. Don't ask 27 is coming from where. This is coming based on this curve fitting. And actually in a simple curve fit program, the simplest one actually you can use Excel or you can use MATLAB, then we can calculate those fitting. Type this parameter A is equal to 27 R squared multiplied by critical temperature squared divided by 64 divided by the critical pressure. Type the values for R, the values of the gas constant R, the value of critical pressure, the values of critical temperature. All of these values are actually calculated from table A1. From table A1, you will see a list of gases there. So depending on the working fluid, depending on actually the problem you have, you can just go to table A1. You will get the gas constant R, the value of the critical pressure, and the value of the critical temperature. Then in this case, we can just substitute here. Then we can calculate the constant A, constant B, substitute in this equation. Then if we have temperature is given and the specific volume is given, then we can calculate the value of the pressure. Or if we have volume, specific volume and the pressure, we can calculate the temperature. So any two parameters we can calculate the third one. We have another modification based on also empirical data, but based on actually wider range actually of tested gases. They tested actually more different gases over actually wider ranges of pressure, temperature, and the specific volume. And each time we have recorded the data, and based on curve fitting, they got actually this modified equation that gives actually the value of pressure as function of temperature and the molar specific volume in this case. So if you have the temperature and the specific volume of the gas, then we can apply this equation to calculate the pressure. But here, شباب, this equation is function of the molar specific volume, V, function of RU, which is the same as R bar, which is the universal gas constant, function also of constant A capital, and constant also B capital, and some constant which is C small. Whatever the naming, we have this definition of the term A capital, function of A0 and A small, and also B capital is function of another constant B0 and B small in this case, based on the curve fit. So if it came to your exam and that will not happen, in this case I will give you this equation, give you also the value of temperature, value of a specific volume to calculate the pressure, and I will give you the definition of the constant A and the constant B. Then from table A34, if you look at this table in your table, we can calculate all of this constant depending on the working fluid. So here table A34, for case of A, actually for the equation, Beatty-Bregman equation, you will find the constant A0 is given, constant A small is given, B0 is given, B small is given, and C is given for different gases. So if the working fluid is air or argon, I will going to this table and read all of these constant, and then we can substitute in the equation. R universal here is given 8.314. This is the universal gas constant. It is given also here the value. And here actually in this equation, the pressure should be calculated. The value of pressure will be calculated in kilopascal. And the molar specific volume is actually calculated in meter cube per kilomole. So the value you will calculate for the pressure in this equation will be in kilopascal. Molar specific volume is in meter cube per kilomole. The molar specific volume, which is, we call it V bar when we have this value bar. V bar actually is equal to the specific volume multiplied by the molecular weight. Molar specific volume is calculated in meter cube per kilomole. The specific volume V, as you know, this is actually calculated in meter cube per kilogram. And to convert from, let's say, given a specific volume, then in this case I will multiply this value by the molecular weight, then I can calculate the molar specific volume. And the molecular weight, as we said, this actually can be calculated from table A1. So from table A1, we can get also the molecular weight is given for any working fluid. So depending on the working fluid, let's say we have air or something, we can go to table A1, we can get actually the gas constant, molecular weight, critical pressure, critical temperature, if needed, yani. Then we can just substitute here. If I need to calculate the molar specific volume, it will equal to the given specific volume multiplied by the molecular weight. So if we have a gas, let's say we have air or something, given actually the value of a specific volume is given and also given the temperature. And we need in this case to calculate the value of the pressure. So using the Beatty-Bregman equation, I need to calculate the molar specific volume, which will equal to the specific volume multiplied by the molecular weight. And given the temperature, then we can just substitute in this equation to calculate the pressure in this case. The pressure will be calculated in kilopascal. This equation, Shabab, as I said, is all constant. You can get from table A34, depending on the working fluid, we can get all of these constant. This equation can be applied accurately up to actually density about 0.8 of the critical density. We said the gas, the error in calculating the actual volume of the gas is very low at low pressure. And as we move actually towards the critical conditions, the pressure is raised, then in this case there will be a problem actually or error in calculating the actual volume using the ideal gas equation of state. But this modified equation can be applied properly up to actually density very close to the critical density or density equal to 0.8 of the critical density. Critical density, Shabab, we have the density is equal to the critical density is equal to B critical divided by RT critical. And you remember the critical condition on the saturation curve. This is the top point of the curve. This is actually the condition at which we have the pressure is B critical and temperature is equal to the critical temperature. Okay, this equation is coming from where we have V is equal to RT and V is equal to specific volume is equal to 1 over density. So based on this equation, density will equal to B over RT, and the critical density is the critical pressure divided by the gas constant multiplied by the critical temperature. B critical, T critical, and R for a given gas, we can just get from table A1. Then we can calculate the critical density. This equation by Beatty Brigman can be applied up to very close actually point to the critical condition, up to density very close or about 0.8 of the critical density. Okay. There is actually a more accurate equation, which is the Bendike-Webber equation. We have here actually more constant in this case, and the equation got more complicated. So if you are given the temperature and the specific volume, we can calculate the molar specific volume with the temperature and apply this equation to calculate the pressure. But as you can see, this equation has considered wider ranges actually of gases over wider ranges of temperature and the specific volume and wider ranges of pressure. And this equation actually can predict the actual volume of the gas, or it can be applied accurately, even actually above the critical condition. It can be applied to a density equal to 2.5 of the critical density. So it can be applied actually even the conditions are higher than the critical condition. So this equation is very accurate equation. But if you look here, as I told you, if it is you are asked to apply it, the equation will be given for you, and all of the constant here, universal gas constant, is given in table A34, which is 8.314. Molar specific volume is the specific volume which should be given, multiplied by some molecular weight from also from table A1. And here actually you will find constant. We have constant A0, B0, and we have constant A small, B small also, and we have constant C small, and we have constant alpha, and the constant gamma. All of these constants are given actually in table A34. Depending on the gas, we can go to the table. Let's say we have actually carbon or something, carbon dioxide. Then in this case, we can read the value of the constant A small, A0, B small, B0, C small, C0, alpha, gamma. All of these constants are given. And the value of the pressure calculated will be calculated in kilopascal based on this equation. V bar is the molar specific volume. The value of the gas constant R universal is given. Then we can apply this equation, and it should result actually in very accurate value. There is another equation, which we call it virial equation of state. This equation actually is equal B, based on the ideal gas equation of state. B is equal to RT divided by V. This is the first term of this equation. But actually this equation, B is equal to RT over V, can be applied at low pressure. At higher pressure, then in this case, we can modify this equation by adding some constant to its polynomial form, some constant A, which is function of temperature, divided by V squared, plus P divided by V cube, plus C divided actually V to the power 4, and so on. So we can add terms depending on the value of pressure. If the pressure is higher, then we can add actually more terms in this case. But actually, all of these terms are constant, A, B, C, D, they are function of temperature, and their value should be 0 when the pressure actually value is very close to 0. At very low pressure, we can apply the ideal gas equation of state without error. B is equal to RT over V. That's why those terms will equal to 0 when the pressure is very close to 0 at low pressure, because the ideal gas equation will be applied in this case. B is equal to RT over V. As the pressure increases, then we can add actually more terms to modify this equation. Okay. طيب, let's see, شباب, there is an example. You can look at this example to see how accurate actually all of this equation. As I told you, if it came to your exam, it will be given for you the equation, and then just you will substitute. Here we need to predict the pressure of nitrogen at a given temperature 175, and the specific volume is also given, and we need to calculate the pressure and to compare it with the actual pressure value, which is 10,000 kilopascal, and calculate the error. Calculate this pressure using the ideal gas equation of state, Van der Waals equation, Beatty-Brigman equation, and also the Beatty-Brigman and Bendike-Webber equation also. We need to calculate the pressure using all of this equation. Okay. So for nitrogen, first of all, I will go to table A1. For nitrogen, I will get the molecular weight of nitrogen, get the gas constant R, get the critical pressure and critical temperature, first of all. Then come to the ideal gas equation of state. B will equal to RT over V. R is the gas constant from table A1. You can check this value multiplied by the temperature, should be in Kelvin, divided by the specific volume given here. Then actually using this temperature and the specific volume, we can calculate the pressure. The pressure value will equal to 13,851 kilopascal. And this is the actual value, 10,000 kilopascal. So in this case, applying the ideal gas equation of state will result in error about actually 40% in calculating the pressure. So the error is about in calculating the pressure. We have learned actually how to calculate the percentage error. It will equal to pressure that we have calculated using any equation minus B actual divided by B actual, which is the actual pressure. And then we can multiply it actually by 100 to calculate the percentage error. And this pressure, 13,850 minus the actual, which is 10,000 divided by 10,000 multiplied by 100. Then we can calculate this error. To calculate this error is about 38.5%. Tab apply the van der Waal equation. Van der Waal equation, this equation is function of constant A and B. Constant A and B a function of gas constant, R, function of B critical and T critical. Then we can calculate A, B. This temperature critical is given. Pressure should be in kilopascal, and the gas constant is given in the table in kilojoule per kilogram Kelvin. So this pressure should be in kilopascal, and it is given in the table also in kilopascal. Okay, no, it is given in megapascal. So we have to multiply by 10 to the power 3 to convert it to kilopascal. Then you can just substitute, calculate the constant A, constant B. You can check those values, and then apply in the modified equation. Then we can calculate the pressure in this equation using the Van der Waal equation. Van der Waal equation, if you calculate the error in calculating the pressure, this error there, then the error will drop down to 5.3%. I apply Betti-Bregman equation. Betti-Bregman equation, this is the equation, which is function of A0, O small, B0, P small, and the constant C in this case. We can get all of this constant from table A34 for nitrogen. Where is nitrogen? This is nitrogen. We can read actually all of this constant here. And then we can come to substitute using the equation, actually the Betti-Bregman equation. We can calculate the term A, function of A0, A, function of A0 and A small, B, function of B0 and B small. Then we can calculate A, B, and C small is given in the table. Then the molar specific volume, the equation is function of the molar specific volume. Molar specific volume is equal to the molecular weight here multiplied by the given specific volume. Molecular weight from table A1, then we can get the calculate the molar specific volume. Then substitute in the equation to calculate the pressure. Now you can see here the error has dropped down to 1.1%. Okay. But if we apply actually the last equation, which is the Bendike-Weber equation, which is this equation, you can get all constant from table A34. Then substitute here the drop, actually the error will drop down actually to less than 1%. That means actually this ideal gas equation of state result in an error equal to 38.5%. When I used actually Van der Waal equation, the error has dropped to 5.3. Using the Betti-Bregman equation, the error has dropped down actually to 1.1%. And using the Bendike-Weber equation, which is the most complicated one, the error can drop down to less than 1%. Okay, but actually, in conclusion, when it comes to your exam or something, what you search for, in this case, I will just apply the ideal gas equation of state. And if required, I will ask you to use the modified equation BV is equal to ZRT. But none actually of those empirical equation will be coming to your exam. But you have to know about it, okay? You can check those calculations, okay? Type some topic else actually you have to end up with this chapter is the reference state and the reference value. Actually, if you look at steam table or refrigeration table, here are the tables here. We said we don't have an equation like the ideal gas equation BV is equal to RT. We don't have this relation there between all the parameters. And in this case, we have to test actually steam or refrigerant under different temperature, and every time we can calculate the pressure, calculate the volume of the steam or refrigerant, and we have to cite those values in the table. We don't calculate, we measure the values. At a given temperature, we measure the value of pressure, measure the value of the volume, and then we can list those values on the table. But what about the values of internal energy? Actually, and the enthalpy and the entropy, those parameters actually we cannot measure. We don't have a device that measures the internal energy, or a device that measures the enthalpy, or a device that measures the entropy. Those actually parameters are calculated based on actually a relation or thermodynamic relation, okay? But actually those equations, we don't have a relation or thermodynamic relation that gives us the enthalpy or the internal energy or the entropy at a given state. Only we have a relation that gives us the difference between any two states, like actually the enthalpy, the change of internal energy or the change of enthalpy. We don't have a relation that gives us the internal energy at a given state. Just we have a relation that gives us actually the difference. If we have a system undergo or change from initial state, one initial state to a final state 2, then we have a relation to calculate delta U, the change of internal energy, which will equal to CV, which is the specific heat at constant volume, multiplied by the change of temperature delta T, which is T2 minus T1. We will talk about this parameter, specific volume, specific heat at constant volume, and how to calculate delta U, inshallah, in chapter 4. Also, but we have here also what we talk about, that we have a relation only to calculate the change, delta. We don't have a relation that gives us directly the value of U or the value of H. The value of U is equal to the specific heat at constant temperature multiplied by delta T. So if we look at the table here, you will find that a given temperature or at a given state, you will find the value of U and value of H and the value of the entropy are given. So that means actually we have to have a reference point. As long as we don't have actually a relation that gives us the value of internal energy or enthalpy or entropy at a given state, then in this case we have to have a reference point at which we can assign a value of 0 for all of these parameters. And this reference point actually is based on the third law of thermodynamics. This reference point for steam is 0.01 degrees C. And at this temperature, we assume the value of the entropy is equal to 0. And like this, we can assume the value of enthalpy is equal to 0 and the value of the internal energy is equal to 0 in this case. Okay? And based on this reference point, we can calculate the internal energy or the enthalpy at any other temperature. We can calculate this value. So at a given temperature, or at a given actually any state, let's say at any point we call it U1, at a given temperature T1, we can calculate U1, in this case, U1 minus U reference. This is the value of listed in the table. But as actually the reference value is equal to 0, at temperature equal to 0.01 degrees C, so this value is 0. Okay? Then we can give you the value of U1 at temperature T1. But the value listed in the table, it's not U1. It is U1 minus U reference, because we don't have a relation to give us U1 directly. We have a relation that gives us actually U1 minus U reference, okay? Which will equal to CV multiplied by delta T, okay? This is the relation that we have. So the value listed in the table is U at a given temperature minus U reference. And the reference value, we put it actually 0, okay? In this case. Let's say at a point 2, we have in this case at temperature T2, we can get from the table the value U2, as we said, minus U reference. Okay? But if I need to calculate delta U, which is U2 minus U1, it will equal to what? The values from the table, because it will be U1 minus U reference, minus U2 minus U reference. Minus will be positive, then U reference will just go together. And this actually is a change of internal energy will be equal to U2 minus U1, which are the values that I can get from the table. U2 at temperature T2 and U1 at temperature T1. That means actually we can play with this reference point. So you can choose any reference point. Okay? And the value of the reference point for refrigerant R134A is equal to minus 40, at which we assign U and the internal energy and the enthalpy and also and the entropy are equal to 0. You can check the table also. At this temperature, those values are equal to 0. And also you can develop your own table. based on your reference point. Just select any reference point, and let's say at temperature equal to 0, the reference actually, in this case, the reference point, let's say it will equal to any value. Let's say equal to, instead of 0, equal to 10 or something. Then it's okay. This is actually the reference point. Whatever the value of the reference point you assign, then in this case, the value of U1 and U2 will be changing. But will the difference be changing? No, the difference will not be changing, because when I say U at temperature T is equal to U1 at this temperature minus U reference, and U2 at temperature T2 is U2 minus U reference. So when I take the reference, the difference between both of them, U reference actually will just disappear, and then actually the change of delta U will be just equal to the value listed, the difference between the two values, which will not be affected actually by the reference point. So whatever the reference point, it will be actually the value listed in the table will be different, but the difference between both will be the same, whatever the reference point. Okay, that's why we may have different table using actually different point in this case, but actually when we calculate the difference delta U, it should not result in any difference, because the reference point U reference, when we subtract the two, it will just disappear. Okay. This is actually, this is what we are concerned about. In thermodynamics, we don't care actually about a system at a given state. Just what we need actually from a thermodynamic system is to generate either heat or work. So we cannot generate heat or work unless actually we have a process change from the system from initial state to a final state. We said in our analysis of heat and work, we said heat and work are actually our process function. They are associated with a process. We cannot generate heat or work unless the system undergo actually a process or a change from initial state to a final state. Okay. Then in thermodynamics, we are concerned actually with the change, not actually the properties at a given state. We need actually to calculate delta U, not U1 or U2. We need to calculate delta H, because if you apply the first law of thermodynamics, it will be Q minus work is equal to delta U. Okay. Then what I need here actually is delta U, if we have a closed system, in order to calculate the heat transfer or the work. Okay. So in our thermodynamics, we concerned about the difference, not actually the exact value at a given state. Okay. Here a very simple example on ideal gas. Here we have a gas that's undergo actually an isochoric process from state 1 to state 2, and from state 2 to state 3 we have the pressure is constant isobaric process, and we need to calculate the final value. So you can apply simply this equation B1 V1 over T1. We have solved an example similar to this one, equal to B3 V3 over T3. Okay, from the initial state to a final state. We have in this case actually B3 is the same as B2. He said the pressure at point 2 is double the pressure at point 1. This is given. This B2 is equal to double B1, and we have the specific volume V3. The volume of the gas B3 is equal to actually 1/3 of the initial volume V1. Then you can just substitute here. You can get the final temperature as function of the initial temperature T1. This temperature, if we substitute in Kelvin, 25 plus 273, then we can calculate the final temperature. So if we have a gas undergo ideal gas, he said here an ideal gas undergo change from one process to another, we can just apply the equation B1 V1 over T1 is equal to B2 V2 over T2 equal to B3 V3 over T3, whatever, and then we can relate the change of pressure, temperature, and the volume in this case. طيب here is شباب another example يعني. He said in this example let's solve it together. In this example actually we have water in a rigid tank. So we have, he said we have a closed rigid tank. Please look at carefully about the naming that are given in your problem. See, he said we have closed rigid tank. So closed, that means the system is closed. That will be very important after we move to chapter 4 and chapter 5. We have to decide whether the system is closed or open to apply the first law of thermodynamic equation. So he said closed rigid closed rigid container. We said closed system, rigid container, rigid vessel, gas in a piston cylinder device. All of this actually means the system is closed system. So the system in this case is closed. And he said actually a rigid tank. So rigid tank or rigid container, as I told you, rigid mean actually the volume is constant in this case. And this is actually the key for the solution of this problem. He said this tank is containing water, so the working fluid is water in this case. So I will be using the steam table. He said this water is in a rigid container. So this is the water. This water actually is existing at pressure B1 is equal to 700 kilopascal. He said actually the mass of the saturated liquid is equal to 1.78 and the mass of saturated vapor is 0.22 kilogram. So as we have saturated liquid and saturated vapor, then this water actually is saturated mixture. Then we have saturated mixture of water. They give you the saturated liquid water, the mass of the saturated liquid, which is what? M fluid, which is equal to 1.78 kilogram. And the mass of saturated vapor is given for you is equal to 0.22 kilogram. Can we calculate something based on mass fluid and mass of gas? Then in this case, based on this, we can calculate the quality of the mixture. X1 will equal to mass of gas divided by mass of fluid plus mass of gas. Mass of gas is 0.22, mass of fluid is 1.78. If you calculate this, you can look here, the value of the quality X1 will equal to 0.11. As the quality is given, then in this case the state is saturated mixture, because this parameter X cannot be applied actually outside the saturation curve. So that means actually here, as the value of X is given, then the state is saturated mixture in this case. But he said actually we have added heat to this system. This system we added heat here. Let's say we add heat. So rigid tank tank is closed. So when we add heat in this case, the volume will be remaining constant. But what will happen to the pressure? The pressure in this case will be this. The pressure P2 here is given is equal to 8 megapascal. Okay, after adding heat in this case. Right. We need to calculate here, is asking to calculate the final temperature enthalpy and the internal energy, T2, enthalpy H2, and the internal energy U2. We need to calculate all of these values. And he asked us also, will the level actually of the water will be raised or reduced inside this tank. So as we have saturated mixture, so we have liquid and we have vapor here. And this is the level of the liquid. We need to see if the level of the liquid will be going up or getting down, okay, after this process. So how we can solve this? We need to calculate the final temperature, final enthalpy, final internal energy. And we are given only the final pressure B2, which is equal to 8 megapascal. So we said to use the table, we have to have two independent and intensive properties. So we need another property here. What is the property we need? Is it given? So it is given actually theoretically, said we have rigid container, so the volume is constant. And this system is closed system. So closed system means the mass is what? Mass is constant. And here the volume is constant. So the specific volume, which is equal to the volume divided by mass, should equal to what? Should equal to constant. The volume is constant and mass is constant as the system is closed by definition, then the specific volume is constant. So that means actually the specific volume V2 is the same as the specific volume V1. But can we get the specific volume V1? Yes, at point 1 we have the pressure V1 and the quality is given. Then the pressure V1 is equal to 700 kilopascal and the X1 is equal to 0.11. So with this pressure value, I will be going to table A5. Pressure is given. I need to calculate the specific volume, so I will get the value of V fluid. Get the value of V gas given in the table at this pressure 700 kilopascal from table A5. Then using those two values with the quality of the value of the quality X, then we can calculate V1 will equal to V fluid plus X multiplied by V gas minus V fluid. If you calculate this specific volume, quality X is equal to 0.11. V fluid and V gas we can get from the table. If you calculate this value will equal to 0.031 meter cube per kilogram. And this is actually the value of a specific volume V1. Okay? So V1 is the same as V2. So at point 2 we have pressure V2 is given and the specific volume V2 is given in this case. Then we have two properties. So we can go to the table with the pressure V2 is equal to 8 megapascal. So pressure V2 is equal to 8 megapascal and the specific volume V2 is the same as V1 is equal to 0.031. Then to a table, again to table A5, given a specific volume, pressure is given with one specific property, specific volume, then I will get UV fluid and I will get the value of V gas from the table at this pressure. 8 megapascal, which is the pressure in the table is in kilopascal. 8 megapascal, which is 8,000 kilopascal. So at pressure equal to 8,000 kilopascal from table A5, I will get V fluid and V gas. And then I have to compare those values with actually the given specific volume. If you compare, you will find this specific volume V is greater than, will be greater than the value of V gas. V is greater than V gas, that means we are in the superheated zone. So the state of steam actually is superheated vapor. And in this case, I have to use table A6. So using table A6 at pressure equal to 8 megapascal, and in this case, you can look at the table, you will find here the volume, specific volume is given. Get down in this table until we reach the value of a specific volume is equal to this value. Then we can read the other parameter, including the temperature, T2 will be given here. The value actually of internal energy will be given, and the enthalpy will be given in this case also. Then we can get actually all of these parameters. Okay. Type well, so that means the state is superheated. So what about the level of the liquid? We had liquid plus vapor. Now it has been converted all to superheated, to vapor. That means actually the level of water just will disappear. So it should get down. Okay. Type, can we represent this process, Shabab, on can we represent this process on the TV diagram? So this process is what? You will be asked actually for any problem, as I told you, to represent this process, any process actually on the TV diagram or the VV diagram. So let's look here for the temperature specific volume diagram. With respect actually to the saturation curve, this is the saturation curve. So first of all, the state was saturated mixture. So let's say actually this is the state number 1. And the process is constant volume. So constant volume, that will be actually just a vertical line. And state 1 actually was in the saturation zone. Then it has been converted to superheated zone. So this is actually the representation of the process. With respect to the saturation curve, we have saturated mixture, and then undergo a process of constant volume. Constant volume in the PV diagram will be just a vertical line, and then it has been converted to superheated. So state 2 is superheated in this case. And typically it is the same representation on the PV diagram. It would be typically the same. Okay. طيب, this is يعني شباب والله what I want to say. But just let's remind you with your quiz. Quiz here we said we have a container, rigid container or rigid vessel with an electric heating coil containing air. Okay. So because I have seen many of you have just made some errors actually in this problem. So شباب, we have rigid container containing air. Okay. This is the rigid container containing air. Mass of air is given 0.27 kilogram. And they said actually to heat up this air, we have electric heating coil, and volt is given, current is given, volt is given here across the circuit, current is given, and they give you the time delta T. I think is it 10 minutes? 10 minutes. So 10 minutes it will equal to 10 multiplied by 60, so it will equal to 600 seconds. This is the time, okay? And we need to calculate, he said we have due to this heat transfer, this electric heating coil will be converted to heat up the air. He said we have the change of internal energy, or the internal energy rises by 42 kilojoule per kilogram. Kilojoule per kilogram, that means this is the specific internal energy. Type. Anyway, this is a closed vessel, so that means the system is closed. So I will apply the equation, first law equation, directly Q minus what? Equal to delta U, or U2, total internal energy in kilojoule, U2 minus U. As the system is closed, mass is constant, so it will equal to mass multiplied by specific internal energy, U2 minus U1. This term is given, which is 42 kilojoule per kilogram. Mass is given 0.27, okay? And we need to calculate the heat transfer, and here we need to calculate the work. So what about the work here in this case? This is electrical work, okay? We have the electrical power is equal to what? You have to make the difference of electrical power and what? Power, electrical power, which is the rate of work dot is equal to volt multiplied by ampere, which is equal to the work, electrical work, divided by time delta T. So if I need to calculate the electrical work, it will equal to the rate of work, electrical power, work electric multiplied by delta T. So the electrical work will equal to volt multiplied by ampere multiplied by the time difference, delta T in this case. This electrical work, if the volt is, V is calculated, the volt is given 120, current is in ampere, delta T in second, this value should be calculated in joule, okay? But here we have substituted, as you can see, and even later on the values from the table will be in kilojoule. Then we have to divide this value by 10 to the power 3 to convert it actually to kilojoule in this case, okay? So in this case, I will be calculating the electrical work. It will equal to VI delta T. V is equal to 120, current 0.2, time delta T is 600, then divide by 10 to the power 3, so on. Then we can calculate this value in kilojoule. Anyway, the value if you calculate the electrical work, it will equal to 14.4. But this electrical work, as I told you, when you apply this equation, we have to look at the sign of the heat transfer and work. If the work is added, is applied on the system, its sign should be negative. If it is produced by the system, then its sign is positive. In this case, the work is applied on the system, so its sign is negative. So when I come to substitute here, it will be Q minus work will equal to minus 14.4. I have to add another negative sign here. Okay, then this equal to actually mass 0.27 multiplied by delta U, which is 42. Okay, then we can calculate the heat transfer in this case. So we said we have to look at the sign of the heat transfer and the work. Either it is added or rejected from the system. This is the sign conversion. Then if the work is added to the system like this case, so the electrical current, when I calculate the value, just adds its sign here, negative sign. So it will be Q minus 14.4. Then this equal to mass multiplied by delta U in this case. Then I can calculate the heat transfer. Okay. So okay, Shabab, by this I'm done actually with the class today. Inshallah, by this actually also we are done with chapter 3. Inshallah, next time we'll have we have to start actually chapter 4.